All right, this is a bit of a tricky one, um, but that's kind of why I like it. So it says in question 6, let me grab a pen first. In a laboratory experiment, lead and an unknown metal Q were immersed in solutions containing aqueous ions of unknown metals Q and X. The following reactions summarize the observations. Okay, so for instance, PB can kick PB PB can kick X out of solution, or because this is single replacement, so this is a singleton, and this is like some aqueous salt. So because PB can kick out X, we know that PB is more reactive than X. And then observation 2, Q cannot kick out X, which means Q is less reactive than X. And so then Q is under X. And then the last observation is PB can kick out Q, and so this just verifies PB is more reactive than Q. And so when it says, on the basis of the reactions indicated above, um, arrange the three metals PB, Q, and X in order from the least reactive to the most reactive. And so this is from chapter 4 last year, the activity series. Now, it's related to what we're doing this chapter because if you'll notice here, these are, sorry, I got this test up. These are standard reduction potentials, and from the top to bottom is the most reactive for the nonmetals. But now metals like to be oxidized, so I gotta be careful here. Let's go slow. Doggone it, I'm not good at the slow stuff on here. But you'll notice is metals, this is the activity series backwards. Most reactive metal is lithium, then cesium, then potassium, then rubidium, because this is reduction potentials and metals like to be oxidized. So I would say how this correlates to the activity series is if you read it from top to bottom, it's the activity series for the nonmetals. The most active nonmetal is fluorine. If you read it from the bottom to the top, okay, it's the activity series for metals, but that's neither here nor there. All right, so back to this. Um, I think that's it for A. And now there's a lot of writing on this page. So the diagram below shows an electrochemical cell that is constructed with a lead electrode immersed in 100 milliliters of a 1 molar PbNO3 solution. So basically you can see we got a lead electrode touching lead 2 solution and it's 1 molar, so standard conditions. And then we have this, we have metal X, which we don't know what it is, immersed in 100 mils of solution. So we have X and X2 in contact. The electrodes are connected to an external circuit containing a switch, which is open when a voltmeter connected to the circuit. When a voltmeter is connected to the circuit as shown, the reading on the voltmeter will be 0.47 volts when the switch is closed. So basically what happens is they'll close the switch. I don't know. The meeting is 0.47. So we don't know what X is yet. Okay, so then I'm going to come down here and okay, so I think that's it. And the next question is write, when the switch is closed, this is the part I forgot, sorry. When the switch is closed, the electrons flow through the switch from PB to X. So basically they're telling you that the electrons are flowing this way. So in other words, this lead is the anode because oxidation occurs at the anode, and this X is the cathode. and all of that entails. And then question 3 is write the equation for the half reaction that occurs at the anode. Well, if you look at the picture, lead is the anode, and so the half reaction is the fact that, and you can see it at the anode, lead, remember, and oxidation means the electrons are on the right hand side, and so it would be lead metal turns into lead ions plus 2 electrons. Remember, oxidation, the electrons are on the right, reduction, they're on the left. We know that the half reaction is one of these two, because if you look in that half cell, there's lead and lead too, but this is reduction. Oxidation is lost, so they're on this side. Reduction is gain, means this guy loses them and this guy gets them. So it has to be this reaction right here. All right. The value for the standard potential of this cell is 0.47. Determine the standard reduction potential for the half reaction that occurs at the cathode. So this is interesting. E of the cell is E oxidation plus E naught reduction. And what's interesting about this one is we know that this is 0.47 volts. Sorry, I'm having trouble writing on here. 0.47 volts. And I'm going to look this up, but we don't know this. So I'm going to go back here because I got this out. If I got to be careful now, I go too fast. If I find lead, and I'm just going to point, here's lead plus 2 going to lead, but that's a reduction potential. So I'm going to flip this around because it's negative 0.13 volts when it's reduced, but it's not, it's oxidized. So we know that this is positive 0.13 volts. I don't know why I'm having so much trouble writing here. And so I'm going to come down here. So then X is going to be 0.47 volts minus 0.13 volts, which last time I checked was 0.34 volts. So that's the answer for I. And determine the identity of X. I'm just going to come here. Very easy. And I'm looking for 0.34 volts. It's right here. 0.34 volts is copper. And so the question is, identify the identity of metal X. It's copper, because that's the only one that has a reduction potential. X is the reduction potential of 0.34 volts. All right, 5. Describe what happens to the mass of each electrode as the cell operates. So if you wanted to do this, let me just do this again. So lead metal is turning into lead ions. Oh, I know what I'm doing. I'm pushing my hand. Okay, so this is oxidation because the charge of lead is going up. And then copper must be reducing, so the charge of copper is going down. And so if I switch colors here, this is oxidizing. This is reducing. So what happens is the equation shows the anode is lead. The anode is lead. Boy, I'm really struggling writing. I apologize. I'll erase this. I'm going to pick this up and see if it helps. Okay, got to go back and grab the pen. So the anode is lead and the cathode is copper, and the lead metal is turning into lead ions. So the mass of the anode is decreasing. And then this shows that the copper metal ions in solution are being deposited, and the mass of the cathode is increasing. Next slide. During a laboratory session, students set up an electrochemical shell shown above. For each of the following three scenarios, choose the value of the correct cell voltage and justify your choice. Student bumps the cell, resulting in the salt bridge losing contact with the solution in the cathode compartment. Is V equal to 0.747 or is V equal to 0? Justify your choice. Okay, V equals 0. That's the answer to the question. Why? If there, I guess I probably shouldn't say there. If the cell, if let me grab the eraser again. Sorry. Let me say what I'm going to write in a minute. Um, if um, if the salt bridge loses contact with one of the solutions, the battery stops working because there is a charge buildup in one of the compartments. So if the salt bridge loses contact with one of the solutions, there will be an imbalance of charge and the galvanic cell or the voltaic cell or the battery, whatever you want to say, galvanic cell, stops um, uh, producing voltage. Basically, in a battery, you're converting chemical energy to electrical energy. All right, now this scenario. A student spills a small amount of Na2SO4 into the compartment with the PB electrode, resulting in the formation of a precipitate. Now, here's the deal. Let's go back to the equation. PB is turning into PB plus 2. And then copper plus 2 is turning into copper, metal. Before I do anything, we're going to cross these out, and you need to understand that Q in the Nernst equation is this over this. Now, in the beginning, Q is equal to 1 because these are each 1 molar. But this says in the lead compartment, they put some Na2SO4, which causes, there's a reaction with the lead. So what happens is, just so that you understand it, Pb plus 2 hits a sulfate ion in solution and they form a precipitate, which has the effect of decreasing the concentration of this. So keep in mind, this is still 1 molar, but in this compartment, this is less than 1 molar. And so what you need to understand from the Nernst equation is that the new voltage is equal to the old voltage, which was 0.47, minus 0.0257 V over N ln Q. But because Q is less than 1, because a number less than 1 divided by 1, because Q is less than 1, the ln of Q is negative. And a negative times a negative is a positive. And so what would happen in this cell is, let me extend this page. Sorry, I got to grab this pointer. And then, so what would happen in this cell is, now all of that is so I can answer the question. Is it less than 0.47 or greater than 0.7? E is greater than 0.47 volts, and your justification would be Q is less than 1. Therefore, the ln of Q is less than 0 or negative. So, so a negative times a negative is a positive. So the voltage would increase. So here's the deal. This is negative. This is obviously negative. So it's going to be 0.47 plus some number, which means it's going to be bigger than 0.47. You don't need to calculate the number anymore. You just have to know that it's bigger than 0.47. Last cell, the student leaves the switch closed. The next day, the student reads the voltmeter. Okay, so what happens is this battery runs all night. Again, here's the battery. Lead is oxidizing, so it's turning into lead plus 2, and copper is reducing. So it's turning into copper. And so what you need to know is, now remember, lead is turning into lead plus 2. So this mass is going down, but this concentration is going up as the battery runs because lead is turning into lead 2. And this is the one that's reduced. And this equation means lead plus 2 is turning into, sorry, copper plus 2 is turning into copper. So this concentration goes down. So basically, as this battery runs overnight, the Pb plus 2 concentration goes up, and simultaneously the Q plus 2 concentration goes down. So the old Q was lead plus 2 over copper plus 2, where this was 1 and this is 1. The new one is this number's bigger than 1, and this number's less than 1. If you take a number bigger than 1 and divide by a number less than 1, Q is obviously greater than 1. And according to the Nernst equation, so E is equal to E is equal to E naught minus 0.0257 over N ln Q. If Q is greater than 1, then the ln of Q is positive. And so you would have 0.47 volts minus some positive number. We don't know what it is, but this is positive, but this is still negative. So some number, and so the voltage won't be 0.47, it'll be less than 0.47 volts. And so to go back up to the question, let me extend the page so that I can write, and then we'll go look. And I just want to see how it's worded, because again, you don't have to do this, you just got to be able to explain it. Is it less than 0.47 or equal to 0.47? Justify your choice. And so the answer is the voltage is less than 0.47. So V is less than 0.47 volts. And justify my choice, say all that. You know, as the battery runs, that increases, that decreases. Q is greater than 1. ln of Q is positive. 0.47 minus a positive number is going to be a number less than 0.47. So justify it like that.